Hi guys, my name is Mark. I'm from Dynex Hobby. Today I'm going to go through the process of dynamic balancing a ducted fan unit. This is the EDF I have. It's a 5-inch fan. I've had it for a number of years now and I've actually gone through an overhaul. So it's a good opportunity to go through how we go ahead and balance it. Alrighty guys, in order to get started in balancing, we need a laptop, of course. So our software runs on a standard Windows laptop. We need a battery to power our ducted fan unit. I tend to use a standard 12 volt gel cell. I have a speed controller which is used to control the speed of the ducted fan via this ESC. We're going to need an impulse unit, of course, which is used to measure the vibrations, and a balancing mount. Now the balancing mount is actually used to allow the ducted fan to sway side to side. Now why is that so important? It's because the impulse balancing unit is actually designed to measure the vibrations on what we call a soft bearing balancing mount. Now there are two types of mounts for dynamic balancing. There are the hard bearing machines and also soft bearing. Soft bearing machines are actually very easy to use. They don't need a whole lot of calibration to function well, and it's easy for hobbyists to actually knock a device like this up quite easily. So to give you an overview of how this works, I'll just take this off. So the balancing mount in this case is just a solid box. The box has two rare earth magnets and these two springs which are actually attached by a bit of blue tack. I'll just bring this closer so you guys can see. Alrighty. So on the bottom of the balancing mount of the base, I've actually put some felt, so that actually stops vibration being transmitted from the box to the table and then back again. That can actually affect some of the results. So that's the base. The actual EDF itself has what I call a sway bar, I suppose, and that is just a square aluminium tube with a steel rod going through that, and it's actually positioned so that it's almost in line with the impeller of the fan. Now that sway bar is actually attached by a Velcro strap all the way around the EDF unit. Now when you actually position the EDF onto the base, the rare earth magnets will actually snap onto the steel bar. So when you attach it, it'll form a nice sort of pivot mount like that. And the good thing about this is it allows the EDF to move in its natural state when it's vibrating. So I'm just going to rotate the base so you can see the side profile of the mount. There we go. So the way this thing is actually arranged is you've got the sway bar, which is roughly in line with the impeller, or thereabouts. Now the rear of the EDF is essentially supported by this foam strip. The idea behind that is to prevent the rear part of the ducted fan from rocking side to side. Essentially what we want is we want the front impeller to be oscillating, so we can actually sense the maximum vibration from that. What we want to do is to reduce any coupling effects from the aft end of the motor to the impeller. So for example, if your motor is slightly imbalanced, you don't want that to be transmitted to the front side of the impeller. So we try and isolate that as much as possible. And so by having this foam strip here, it kind of stops that motion from happening. So ideally, when the impeller is running at speed, it's oscillating like this, and the sensor, which is located directly above, it's sensing that vibration. So I'm just going to rotate around now to show you how the sensor is installed. So the sensor, I'll just take that off. So when you receive this in the kit, that's the accelerometer. The accelerometer is just a sensor for measuring acceleration, of course, in one direction in this case. The direction of the sensor is in line with the tail of the lead. So the tail of the lead is running in this direction, so the sensor will be measuring the vibration along the tail direction. So we can go ahead and mount that on top of the EDF. Now I'll mount that on top there. Now ideally we would want to mount the sensor directly above the plane of the impeller, so that the maximum vibration or unbalance from the impeller is transmitted directly in line with the accelerometer. So that's mounted on top of the impeller. It's a good idea to actually tie down loose leads. So what I tend to do is I use a bit of blue tack, which is there, mount it to the side, and tie all the leads down. For two reasons. You don't want the lead to fly inside the impeller, which is a hazard there. You want to tie all that up. And the second reason is that the vibration of the lead onto the case of the impeller could also jeopardize the true vibration or imbalance measured by the accelerometer. So that's installing the accelerometer onto the EDF. With this single plane method, we need a infrared sensor. Now that infrared sensor measures something called a phase measurement. And what that phase measurement is essentially is the offset of the imbalance relative to a position in space. So what that means is if we have an imbalance on the impeller, let's say for example the imbalance can be simulated by, I'll just get a bit of blue tack. Let's say for example there's an imbalance on the impeller which is located say here. So what the infrared sensor does is it measures the relative angle between the maximum vibration, in this case where that piece of blue tack is, relative to the reference point on this hub. So when I install the infrared sensor, it has a very short range. The range is normally between 3 and 5 millimeters from the hub of the impeller. So when I install that, I like to install it so that it is normal to the hub and not too far away, so that when the line passes the infrared sensor, it should give you a nice pulse signal on the screen. Now you will need some other items, guys, to carry out the balance for the single plane method. The first item is actually a set of scales. Now these are jeweler's scales. They're very sensitive. They go down to, in this case, 0.001 of a gram. Essentially you need that kind of accuracy when you measuring trial weights or balance weights for EDFs. The other thing you would need is a set of calipers, and that's just measuring the diameter of the hub, and I'll show you the purpose behind that later. And probably a packet of blue tack. This is available in Australia. I'm not sure about overseas, but essentially it is like a very sticky sort of clay or moldable clay material. And it's very handy to use. It's reusable as well, up to so many times before it loses its tackiness. So they're the main items that we need to actually get started in our single plane method. So I'm going to demonstrate assembling the setup and go from there. Alrighty. So to install the impulse onto the system, there's our impulse, and that's the cable that comes with the Impulse. So install that into the Impulse, and the other end, free end, goes into a free USB port onto your laptop or PC, whatever you are using. So I'll install that now. When you install it, you'll get this super bright LED, which indicates that the system is working. Now, when you install it for the first time, what you'll find is that Windows will automatically detect the device as a USB audio device and will automatically install drivers. Now, if drivers don't automatically install, then there's essentially an issue maybe with the setup of Windows, or maybe there's a firewall issue on your laptop or PC. So, but in general, it is very reliable. Once you install it, it will automatically detect the drivers and self-install. So once that is done, now you want to connect up the sensors. So I'll just rotate the camera. All right, so the accelerometer goes into accelerometer number 1, and that gets positioned like this. So the black lead faces the top label of the Impulse, so I'll plug that in. And for the infrared sensor, again, the black lead of that faces the top label. You want to switch the front switch here, or the select switch, to plane 1. We only have one sensor for this analysis, which is a plane 1. Alrighty, so that all is set up, ready to go. You want to make sure that the position of the infrared sensor is about 3 to 5 millimeters away from the hub. You want to fix this securely in place, just so that when the EDF is running, it's not going to run into the fan and actually, debris flying everywhere. For the ESC, I've got my 12-volt battery. I can connect that up. In my case, it'll start beeping. And ready to go. Now, just a side note, guys, about those who have purchased the laser sensor. Now, laser sensor, it's quite a handy piece of kit to have. So it allows you to position the sensor away from the proximity of the hub. But there is a bit of a catch to how you set that up, so I'll just demonstrate that. So I'm going to remove the infrared sensor and plug in the laser sensor. As soon as you plug it in, you'll see, I don't know if you can see that on the camera, the green dot next to the yellow light. Right, so when that is actually installed onto the hub, I'm not sure if you guys can see that. Yep. There's a bit of a catch in terms of how close you set this to the hub. So essentially what I find is that when the sensor is positioned at a slight angle and maybe 10 to 15 centimeters away from the hub seems to be a sweet spot. But what you'll notice is that when you run the balance in the software, you'll find that occasionally the RPM will either jump up and down or won't register at all, and it's because the distance or the angle that the laser makes to the hub is not optimal, and so that the software can't see a true pulse signal. So the way around that is to position the sensor closer or further away, or even rotate the angle of the sensor so that you get a very good return signal. Okay, so I'm just going to disconnect that now and reconnect the infrared sensor, and we'll get started on the balance process. Alright, so now we can get started. So I'm going to open the Dynex Hobby software. Click I agree to the warning. Okay. So the software is broken into 3 main parts. We have our single plane balance, our 2-plane, and our tools. For today's balance, we're going to use the live single plane balance, which is really handy because it encompasses a lot of the features from the other elements of the software into one application. So I'll click on the live plane balance, which is down to the left hand side, click OK. And then we have it. So I'm just going to move that to the side, and then I'm going to select the main window and just minimize it. Okay, so to set up the analysis or the balance in this case, I'm going to go through the tabs at the top. So as you go into the software, it has automatically detected the impulse. But if it doesn't detect it, what you can do is you can click on Devices and then select Microphone USB Audio Device. Click OK and then click Start. One of the first things to do when you're in this mode is to zero the sensors. So at the moment, the system is measuring I guess the noise level from the accelerometer. So you'll see it sort of jumping up, 0.1 to 1 millivolts. So with the system at rest and not touching that, what I'll do is click on 0, and that will zero the sensors. Now it's a very sensitive system. As soon as you tap on the table or bump it, you'll see the vibration level creep up. Next thing to do is to look at the Setup tab, and the Setup tab actually accommodates for various types of balancing setups. So in this case, the EDF unit is actually a simple balance method, and the overhang thin disc method is used for a thin disc that's connected to a long shaft with 2 bearings, for example. So we want to look at our balance criteria. So in this case, I'm going to be running the EDF around about 50 Hertz or about 3000 RPM to do the balance. And you need a reasonable speed in order to measure the imbalance. If the speed is too low, you seem to be measuring a bit of noise, and if it's too high, then it can be a hazard, I guess, to the operator. Next thing to do is to enter the rotor mass. So this is the mass of the impeller, and also the I guess the shaft of the motor. But in this case, I'm just going to put in the impeller mass, which is about 150 grams or thereabouts. The balance grade is how fine you want to balance to. Now, for something like a ducted fan unit, 2.5 is actually super fine, but I tend to use something in an order of about 6.3 millimeters per second, which is reasonable. The other items here, so the plane 1 to bearing B distance and the bearing distance and the plane 1 mass radius. So I'll just talk about the plane 1 to bearing B distance. That's not really required for this type of setup, and the bearing distance is also not required for this type of setup. So we just leave them as they are. The service RPM is the speed at which, the maximum speed at which the EDF is expected to run. So in my case, I'm just going to use an arbitrary value here of about 25,000 RPM. The plane 1 mass radius is the distance from where the trial weight is going to be installed to the center of the hub. So in my case, I'll just get my verniers. So I'm going to measure the diameter of the hub is about 46 millimeters. So my mass radius distance will be half that, half the diameter. So it would be 23 in this case. And what that means is this is the distance at which the trial weight is going to be positioned when you do the calibration process. Now the direction at which we spin the EDF, in this case, is in anti-clockwise direction. So I'll click on that. There is another plane which illustrates or demonstrates the signal. Now there's two signals. There's one from the infrared sensor and the other one from the actual vibration sensor or the accelerometer itself. Generally what I tend to do is turn channel 2 off because its signal is so much larger than the vibration. There is another plane for measuring frequency, and that is it just shows you the main imbalance frequency, and if there are other frequencies which also appear in the spectrum, that could indicate there might be other issues associated with the EDF. There are some gauges as well where you can measure or see the phase, vibration and the speed of the EDF. And in the advanced setup, a lot of these factors or parameters can be left as they are by default. The only thing that you really need to change here is how you want to correct the imbalance. In this case, I tend to use add the weight rather than remove, because it's easier to add the weight and see what effect it has before you go and actually modify the EDF. So they're the main parameters that we need to set. So I'll just go back to the main live window. Now, what you'll see on the bottom right-hand corner of the window is something called the quality plane. And what the quality plane is actually doing is it's measuring the residual imbalance associated with your setup. So what do we mean by a residual imbalance? Well, everything that rotates or every item has what we call a residual imbalance, which is essentially the theoretical offset of the mass of the rotor compared to the center of the rotor. So for example, if we do our best to try and balance the rotor, there will be in theory a small amount of mass offset from the center of the rotor, which will always exist. It's almost impossible to remove the residual imbalance, but we can reduce it to a very, very small value so that it has very little effect on the total vibration of the EDF. So if I was to demonstrate that, the residual imbalance on the EDF would be, for example, this piece of blue tack. So in theory, if there was still residual imbalance, it would be this piece of blue tack located at a certain radius from the center of the axis of the EDF. So for example, if I had a 5 gram residual imbalance of the EDF located, say, 10 millimeters away from the center of rotation or the axis, then my residual imbalance would be 50 gram millimeters. And so the quality limit actually identifies or actually evaluates what that residual imbalance does after you do your balance process. Now we're actually going to get started in the balance procedure. Now to get started, you actually need to calibrate the system. The system needs to be calibrated so that it actually knows what an imbalance is and the size of the imbalance as well. The calibration also, it builds a mathematical model of the dynamics of your EDF and the whole mounting system. And that mathematical model is actually used later on to evaluate, well, what is the correction weight we need to apply to the EDF to reduce the residual imbalance. So getting started, there's a button called Calibrate on the center bottom of the console there, and another window will pop up, which is called the single plane calibration, and it's broken into steps on tabs located on the side of the window. So there's introduction, which basically identifies your setup and how how to perform the calibration. So we'll progress into step 1, and step 1 says to set up the rotor for the tests, and what we want to do is we want to run the EDF at our test speed and measure the existing vibrational level without any weights or anything applied to the EDF. So we'll go ahead and do that. Alrighty, so in step 1 we recorded our original vibration without any weights applied. Now we progress down to step 2, and step 2 says apply trial weights onto the EDF, and in this case we're actually going to apply it in line with the white marker on the EDF hub. So I don't know if you can see it, our white marker is right here, right there. So I'm going to take my scale, turn it on, and I'm going to apply a piece of blue tack onto the scale and weigh that. So the weight of my blue tack is about 0.2 grams. I'm going to take that piece of blue tack and I'm going to apply it to the hub. Now I'm applying it not at the front of the hub, but more in line with the impeller. So sitting in line with that marker there, but further back, so it's in line with the plane of the impeller. Alrighty. So now what I'm going to do is enter the weight into the calibration window. So the trial weight is 0.2 grams. So it's 0.2 grams. The radial position of the trial weight, as we measured previously, is 23 millimeters. So 23 millimeters from the center to where that trial weight is located. It's the radial direction that way. So I'll put 23 in the window. So once that is done, the phase angle or location of that trial weight is actually 0 degrees. In other words, that trial weight is located at an angle 0 degrees relative to the white marker on the hub. If that trial weight is applied in any other position, say for example if it was applied say here, it'll be 90 degrees, 180, 270, etc. But just to keep it simple, we tend to apply it at 0 degrees. So once that is done, we can move to step 3. And step 3 says, okay, so you've mounted your trial weight, so now we're going to run the EDF at the test speed and measure the imbalance there. So we're going to do that. Okay, so we've taken the measurement and so we'll switch to the final tab, which is called the calibration factors tab. And so in the calibration factors tab, we see there's a whole bunch of text boxes there with which says click calibrate. So we'll click calibrate and a whole bunch of numbers appear in there. So once that is done, we'll click on done and we'll go back to our main balance window. Now I'm going to switch to the advanced window or tab, and what you'll notice is that the calibration coefficients have now been transferred to the advanced tab. So what these coefficients do is it defines the mathematical model of the imbalance of the system. Now, that mathematical model is only applicable to the setup that you have. Now, if you change anything on your setup, for example, if you change the type of mount that you have, if you change the position of your accelerometer, change the position of your infrared sensor, if you change anything relative to how this is configured, then your mathematical model may not be representative of your configuration. So it's okay to take the EDF off and then put it back in the same position and rerun the balance, that's fine. But if you're going to change the configuration in any other way, then the balance won't work. Alrighty, so now we've actually got our system calibrated, set up, ready to go. Now we're going to actually do our balance run. Okay, so to do our final balance run, we'll switch back to the live window. Okay, and we'll make sure that our trial weight is removed. We don't need that anymore because the system is calibrated. And we're going to run the EDF at the test speed and measure the vibration level. Alrighty, so we've measured our vibration level, and the software has gone back and analysed the data, and it has actually identified that we need to apply a 0.1 gram weight, or correction weight, to the EDF impeller, or to the hub I should say, in a direction which is say 100 degrees counterclockwise to the location of the white marker. Now, if you look on the quality plane, what you'll see is that the system is set up to actually balance to a quality limit of, say, 0.361 gram millimeters, which is quite fine, actually. So, with our current EDF in its current state, it has a quality limit of about 2.47, which is quite high. So essentially our EDF is imbalanced, and we need to bring that back to an acceptable level. So what we can do now is weigh our 0.10 gram correction weight and apply that to the EDF, and then check our final balance or residual imbalance. So that is located approximately in this location. It's about 100 degrees counterclockwise. Okay, so our correction weight is applied to the EDF now, and we're going to give that another run. Alrighty, so with that correction weight applied, we actually got the vibration level way down. So our quality limit for the final balance is about 0.2254, which is highlighted in green, which says, hey, you know, you've reached an acceptable balance level for your EDF setup. So you could continue trying to fine-tune the EDF if you like, to try and bring the imbalance level further down. But what you'll find is that the system gets a lot more difficult to fine tune because the vibration signal gets smaller and smaller. So it's very hard to chase that the perfect balance solution. So there you have it, guys. That's the single plane balance method. So we reduced the imbalance or residual imbalance of the EDF down to an acceptable level. So now we can go ahead and mount that on a test stand and give it a run up to full speed. Now, just some safety warnings there. Always stand away from the impeller, of course, when you run at full speed. Wear safety gear, goggles. Probably have a safety guard around the EDF as well, in case there's an issue and the impeller, there's debris that goes flying everywhere and you don't want to be in its path. Now, one thing to note about the imbalance level, as the imbalance level gets smaller and smaller, the vibration signal gets smaller as well. And what you'll find is that as you keep chasing that finer and finer imbalance level, it gets a lot more difficult to do. So as you start progressing in getting a new balance solution, you'll find that balance solution will start hopping around the dial, so to speak. When you hit that state, then you know that the system can't resolve that imbalance level. So there you have it, guys. If there are any questions, feel free to post down below and I'll be happy to answer them. Thank you.